Hello, physics and perhaps calculus students. We're going to talk here about differentiation, which means taking derivatives of functions and why we do that, and well, how we do it. In a very formal sense, how we do it. In more of a procedural sense, how we do it, and some definitional things as derivatives apply to physics, specifically in a kinematics or motion context. So let's talk about how we can, or how we evaluate the instantaneous velocity of an object at some time. All right, I'm providing you've been provided here with a graph of an object's position as a function of time, and from that we want to be able to find an instantaneous velocity. Well, many of you, maybe introductory first year physics students know / remember that if you want to evaluate graphically something about instantaneous velocity, you look for slope at an instant. So for example, at this instant, maybe we'll call this like t1, we could say a slope of this thing looks something like that, right? We could say at a later time, at a different time, say like right now, maybe at t2, we could say a slope looks, I don't know, sort of like that. You know, forgive me if my slopes aren't just right. Whoops, again. Yeah, that's better. Good. You know, and there's others. Sure, fine. You get it? Here's T2. What are you? There you are. So, as we perhaps know, qualitatively from here, we can tell a couple of things. We can tell that this object has changed direction because the slope of this line has changed. Changed sign, right? The blue slope is positive, the green slope is negative. I would argue those slopes are about the same magnitude, so I would say that these objects are traveling at about the same speed at time t1 and t2. Just in opposite directions. You know, there are special times like right here, right now-ish, where we can see that the slope of this is basically 0, and that object is instantaneously stopped. All right. So what we do here is we usually say we take well, let me do this. We usually say that instantaneous velocity equals slope of tangent of an xt graph. Right? Yeah. Well, okay, sort of, but sort of not. All right. So let's talk about the process that we're actually going through when we find quote instantaneous velocity. All right. So let's say that we want to find the instantaneous velocity of this object at this time. This time, let's say right now, that time t. So what's the process that we actually go through? Well, I mean, velocity by definition is defined to be the rate of change of position. All right. So what that means is that saying the rate of change of position, right? We're really saying that there is an average velocity that something has that depends on its change in position and how long that change in position took. All right. And that's really the definition of a slope, right? Especially for this graph. The delta x is a change in y value stuff, the delta t a change in x value stuff. So if we want to know the instantaneous velocity at this time t, what we're really saying is, well, how far did, I mean, the paradox of, quote, the instant is that we want to know a velocity at an instant, but there is no such thing as that, because velocity assumes that things have changed, that position has changed. And one of my favorite statements is that a universal truth is that change takes time. Things can't change if time has not progressed. All right, so what we're really doing is we're really saying if we want an instantaneous velocity, well, we kind of have to look a little bit this way of t and a little bit this way of t, and let's take that little section of this graph. All right, so that section of this graph looks like that ish, right? And what would be nice is, well, I don't know, how about, time t is in the middle of that, so here's time capital T. But what if we can start to zoom in on that, and now that in this box starts to look, a little straighter and a little straighter. So that looks, kind of, well, it's still a little bit curvy. All right, but we're down now to a really, really small delta t. All right, and the quote instant, I mean, that really does mean at one, well, what it doesn't mean is at a single time. What it means, an instant is really an infinitely small amount of time. Okay, so we've gotten down to where this might be, from here to here, a measurable delta t, and from, here to here is now really a whole lot smaller delta t. And then maybe we even zoom in on a little section of this one. I won't redraw, but we have to imagine that we keep doing that and doing that. And what we get down to is what I'll call, well, not what I'll call, but what is referred to as not a macroscopic measurable amount of time, but an infinitely small amount of time, an immeasurably small amount of time. That's an instant, right? We like to think of instant as one specific time, but there's kind of no, I mean, there is such thing as that, but as it applies to talking about how things happen as functions of time, we can't really talk about a single instant. But what we can talk about is a really, really, really small amount of time dt. And here's the thing, we usually say, right, we want to know what the instantaneous velocity is, so what we do is we take the slope of the tangent, right? But we can't really take a tangent, because a tangent only touches that curve in one place. And what we want to know is how far has this object gone from, well, this time to this time. All right, how far has it gone? Well, it was here, and later it's here. And this is a tiny little change in position. We'll call that a dx. And again, we have this little tiny change in time from now to now, and that's our dt. So this instantaneous velocity we refer to as dx dt. It's like this, but with very, very small amounts of time, and therefore very, very small changes in position. Okay, it's not really an instant, but what is an instant, right? So that's that paradox of the instant thing that I refer to. So it's also worth noting that when we say we take the slope of a tangent, well, we don't. Because what we actually do is take the slope, this is going to be hard to do correctly, so you might have to bear with me, but we're going to take the slope of this line that touches the curve in the two places, the two green dots that I've located here. So that line, nope, but bear with me. That line, that's a little better. That's a, wait. That's probably gonna, yeah, that's a beaut. All right, so that line actually touches that red curve in two places. At our first position, at our first time, and at our second position, at dt later. All right, so that's actually, I mean, formally, technically what we're doing is we're taking, when we say slope of the tangent, well, it ain't a tangent, right? It's actually a line that touches the curve in two places. It's actually the slope of a secant. That doesn't matter procedurally. It's just worth saying. All right, because again, the tangent touches at one instant. We have to talk about what has happened as a function of time. So we have to touch in two places. We have to evaluate this function at two places and see how far this thing went, or what the change in position was, I should say, and how long that took. Okay? Okay. Now, how do we actually do that? Well, okay, I'm going to take, we have to talk about, definitionally, so you calculus students have seen a definition of what, maybe seen a definition of what a derivative, how you calculate one. But if we go back to our little curve, and we have that part of a curve, we're zoomed way in now. All right, what we have is a thing here, a place here, x at some time, let's call it t. And then later we have this, that's x at t plus some delta t, right? And then here is this instant is time t, and this instant is time t plus delta t. So definitionally, if we want to take the derivative of this function, or finding, in this case, well, generally, I know we're talking about an xt, so the derivative, well, really is the instantaneous velocity. But generally, we can talk about derivatives as generally instantaneous rates of change. So that allows us to get away from only applying this to position and velocity, but other stuff. And sometimes rates of change can happen spatially as opposed to temporally. Temporally means as functions of time. But sometimes there will be things that we talk about how do functions change over space, spatially. Anyway, what we want to do, if we're going to take the derivative of this function, well, if we say dx dt, that by definition is the limit as delta t approaches 0 of delta x over delta t. So what's delta x? Well, delta x is x final minus x initial, right? So that is, let me keep this, delta x is x final, t plus delta t, minus x initial at our original time, all over delta t. All right, so definitionally, if you're a pure calc student, you've probably seen something with f of x and f of x plus h or something like that. I don't know, something. But this is how we're going to do, in this case, a derivative of a position function. All right, so quite literally, there are easier procedural ways to do this, but we're going to step through brute force application of this expression with some real functions and see what shakes out. Okay, so I'm going to copy this stuff. Now I'll just write it again. I got spare time. So let's take, by brute force, the derivative of this simple function. This happens to be the position of an object as a function of time. All right, and we want to know the derivative of this function. So definitionally, if we want to take that derivative, if we'll say that dx dt is the limit as delta t approaches 0 of x of t plus delta t minus x of t over delta t. So let's break this into parts and actually do what it says to do. Let's try this part first. Let's evaluate this function at time t plus delta t. So that means everywhere we see a t, we insert the value t plus delta t. So this first part, call that 1, gives us 5 t plus delta t squared. Yeah? I will FOIL and distribute at the same time. That's plus 10 t delta t plus 5 delta t squared. Yeah? Let's do this part. Well, that part's easy. call that 2. That is quite simply 5t squared. If we then do this and subtract one from the other, the second from the first, what we end up with, I should be putting the 3 in here, right? I don't know, is, well, this thing minus this thing, and all that happens is those go, and we get 10t delta t plus 5 delta t squared. And then if we do the whole darn thing, what we get is the last number 3 expression, 10, well, let me do this. We're going to do quite literally the whole darn thing, I guess. Let's do the limit also. Let's do the limit as t delta t approaches 0 of 10t delta t plus 5 delta t squared over delta t. Notice delta t divides away with that and with one of those. So we've got the limit as delta t approaches 0 of 10t plus 5 delta t. Well, this term approaches 0, and we're left with yeah, it's okay. Now, let's talk about some physical significance. This sort of looks like if we say x of t equals 5t squared, that looks a lot like right? Particularly if v naught is 0. Think of a v naught t plus 1/2 at squared. So if v naught is 0, 1/2 a could be 5. And notice that v instantaneous is defined to be that instantaneous rate of change of the position function, and that says 10t. And doesn't that look sort of like v as a function of t is at, right? As long as v naught equals 0, right? Because I'm thinking v as a function of t is v naught plus at. And look, we said, okay, well, 1/2 a must equal 5. That means a is 10, and look, at. So we have sort of, I guess, proven that kinematics equations jive with instantaneous rates of change, and they agree with what calculus defines velocity to be as it compares to position. Okay, let's formally differentiate this expression and prove that we get what we're supposed to get. What I mean is, let's say that dx dt, by definition, of x of t plus delta t minus x of t over delta t. Okay, let's go through our first operation. So we have to evaluate this function at time t plus delta t. So we get v naught t plus delta t plus 1/2 a t plus delta t quantity squared. All right, that's going to give us, distribute v naught t plus v naught delta t plus, let's FOIL and distribute the 1/2 a, 1/2 a t squared plus 1/2 a times 2d delta t. So that's simply a t delta t plus 1/2 a delta t squared. It's okay. Well, this part is simply the expression that we start with. That is v naught t plus 1/2 at squared. If we were to take the difference, that goes with that, this goes with this. So 3 says we have V naught delta t plus AT delta t plus 1/2 a delta t squared. If we do the whole darn thing and take that limit, of, let's see, V naught delta t plus AT delta t plus 1/2 a delta t squared over delta t. Okay, bang, 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 bang. So now we're taking the limit as delta t approaches 0. I'll just write it one more time. Of V naught plus AT plus 1/2 a delta t. And this term, as delta t approaches 0, that term approaches 0. Oh yeah, right. Look, when we differentiated the position as a function of time, what we get is our known expression for velocity as a function of time. Okay, so the kinematics equations are what they are because of definitionally how instantaneous rates of change work. Now, this is a even more formal expression for the position of an object as a function of time. What we really have to have is, if we want to know where something is at any instant, we also have to know where it started, right? So we're used to perhaps seeing delta x is V naught t plus 1/2 AT squared. That's true. We've taken the delta x is the x at some instant minus the initial position, and then we're left with the rest. Okay? It's worth noting that what this really is, or what this really contains without saying it, is almost a term in here that is t to the 0, t to the 1, and then t to the 2. Okay? And what's worth noting is that since we know v as a function of t is, well, V naught plus AT, this is sort of like saying 0 times x naught plus 1 V naught times t to the 0 plus two times 1/2 a t to the 1. Agreed? That's the same as saying Vt is V naught plus AT. All right, but it's worth noting, look, I mean, what we are really doing is we're taking this and multiplying it by the coefficient there, and we're taking this and multiplying it there. We're taking this and multiplying it there. And then we take, well, here at least, we take this and we drop it by 1. Here we take this and we drop it by 1. Here, maybe we did, and this is negative. There's a -1 here, but since there's a 0 in front, that doesn't matter. So as we talk about what's called an algorithm, that means a kind of standard calculation of how you do something. What that means is we can take a function. Let's say that there's a function f of x equals cx to the n. Well, and that could be any old function, right? If we want to take its derivative, df dx, what we do as a sort of algorithm is we say, well, that's n. We take this and we multiply in the front, and then we take this exponent and knock it down by 1. Okay, so sure, you can take derivatives this way if you'd like, but it's a little bit of a mess, right? What you can do instead is apply this algorithm that works for lots of kinds of functions, not all of them. All right, it doesn't work for a few kinds of functions. It doesn't work for sines and cosines. It doesn't work for exponential functions. Sorry, it doesn't work for special kinds of exponential functions. But it works for lots of functions. Okay? So here's what you should do. You should prove, we now know that if we've got definitionally this function, x of t is dt cubed, well, algorithm says that dx dt is going to be 3 dt squared. That's the algorithm, right? Take this number, multiply in the front, take this, subtract 1 from it. What I want you to do is go the brute force path, all right, and do the, well, definitionally dx dt is the limit as delta t approaches 0 of blah, 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 and prove that you get this. It's a pain because you're going to have to cube stuff, right? You're going to have to cube a t plus delta t term, but, you're advanced in algebra, so that'll be some brute force. But just prove that it works. And we don't have to only have the standard sorts of functions that we're familiar with from a kinematic standpoint. Okay? When I see you next, you'll have that answer borne out. Cheers.